Today we're taking a look at section 9.4 on the geometry of triangles, and we'll be looking at congruence, similarity, and the Pythagorean theorem. Please bear with me on this recording. I'm getting over a sinus infection, so I'm a little bit stopped up, and my voice is a little weak, but hopefully we can manage to get through this. First of all, triangles that are both the same size and same shape are called congruent triangles. You may remember from geometry in high school that you did a number of proofs showing that triangles were congruent. And there were several ways you could do this. You could do this by side, angle, side, angle, or side, side, side. Now, actually, we aren't doing any proofs, but we just wanted to remind you of what you did in high school. Now, let's take a look at important statements about an isosceles triangle, and as usual, my drawing has disappeared, so I'm going to try to put it in here, hopefully, so it looks reasonable. Okay, so we have an isosceles triangle. The base angles A and C, so we're talking about these angles right here, are both equal. The angles ABD and CBD, so that's this one, are equal. And both of these down here are right angles. And of course, since it's isosceles, the two sides are equal. Similar triangles are triangles that have the same shape but not necessarily the same size. What happens is if we look at similar triangles, we will find that the angles have the same measure and that the sides are proportional, what we call proportional. That is, the ratio of the sides always gives us the same number. So I'll go ahead and do this. So those would be similar triangles. Now, angle. If the measures of two angles of one triangle are equal to those of two corresponding angles of a second triangle, then the two triangles are similar. And that comes from the fact that the sum of the measures of the three angles is equal to 180 degrees. So if we have two the same, then the other angle would have to be the same in a similar triangle. Okay, now let's talk about the sides being proportional. And what I want to do is work an exercise. This is number 24 on page 574. It says we've got a picture of a large triangle with A, B, and 75. And then we have a smaller one, which is 10, 20, and 25. And we can see they're similar by the way the angles are marked. Okay. So what we do is we look at the ratio of 75 to 25. Note that we could reduce that to a ratio of 3 to 1. So, excuse me, the base of the large triangle is 3 times as long as the base of the small triangle. So when we're going to look for the length of side A, what I'm going to do is I'm going to put large over small. So 75 over 25, or 3 over 1, equals large to small, A to 10. We do our cross products. We get A is 30. If I do the same thing for, change my color here, B, 3 to 1, that's large to small. b to 20. Cross products, we get b is 60. Okay, let's do number 36. This is an application problem dealing with similar triangles. The Santa Cruz Lighthouse is 14 meters tall and casts a shadow 28 meters long. Okay, let me turn to my picture. Okay. Alright, so here's our lighthouse. Okay. And, well, I'm not doing a very good job of that. Here's the lighthouse. And it's casting a shadow that's 28 meters long, whereas the lighthouse itself is 14 meters tall. The lighthouse keeper, on the other hand, is casting a shadow that's 3.5 meters long. So we want to know how tall the lighthouse keeper is. I'm going to do large to small. So 28 to 3.5, that's the two bases. Large to small. Make sure that looks like a point there. Equals 14 to x. So 28x, do my multiplication over here since I don't have my calculator handy. So that's 49. So I come up with the lighthouse keeper being 1 3/4 meters tall. Okay, and last of all, we have the Pythagorean theorem. If we have a right triangle, and the two shorter legs are labeled A and B, the third one opposite the right angle called the hypotenuse, labeled C, then what we know is a squared plus b squared equals c squared. Okay, make sure you watch the sample problems before you do the online homework.